Hello, good morning again. Can everybody hear me? Okay, let's start. Good morning, everybody. I'm Kevin. I'd like to welcome you to this webinar about torsional vibrations in turbo machinery. We will speak about the key aspects about torsional vibrations, and today we will introduce our brand new product, Torso Detect. Before we start, I'd like to introduce our speakers, Nicolas Cherouy, Fritz Petit, and Enrique Moraga. Nicolas is our head of sales. He will give a brief introduction about Laberlec and our activity domains. Fritz Petit is a PhD in mechanical engineering and our expert on torsional vibrations. He supported many RCAs related to torsional vibrations and supported the development of our own torsional vibration protection system. Enrique Moraga is our business development manager with 15 years sales experience in thermal generation, and he's responsible for all our clients outside ENGIE. He will have the honor and the pleasure to introduce our brand new product and a game changer in the world of assessment of torsional vibrations, Torso Detect. Now, before we start, a quick word about the interaction during this webinar. We are pro interaction, so we welcome every question. Please use the Q&A box actively to ask questions. There are 2 or 3 Q&A moments depending on the number of questions, and we are happy to receive them in the Q&A box. After the webinar, you will receive a written answer to every question. So, on the program of today, we will speak about torsional grid interaction. This is about the why and how your asset is at risk. Then, secondly, we will speak about the basics. Then, some case studies will follow. And at the end, we will do the introduction of our brand new product, Torso Detect. Now, let's get started. Nicolas, the floor is yours.
Thank you, Kevin. So let me introduce you briefly Laberlec. So we are a research center providing a wide array of services that stretches all along the electricity value chain. And we focus on the 3D of the energetic transition, which are the decarbonization, digitalization, and the decentralization. Laberlec has a global presence with offices in Germany, Chile, Thailand, and in the Middle East. And our customers are based in 60 countries. So with more than 60 years of experience on assets of many types and brands, we are totally independent, and we provide to our customer neutral recommendations. As part of ENGIE research, we dispose of more than 20 thematic labs with deep expertise in disciplines such as water chemistry, CO2 capture, cybersecurity, energy efficiency, remote monitoring and maintenance, and of course, finally, vibration and mechanics. That will be the topic of our webinar today, with the introduction of a new Torso product, Torso Detect, that our team of experts will present to you now. Thank you very much.
Thanks, Nicolas. So let's now get started with the first part, the torsional grid interaction. The lightning strike, I think we're all aware of the potential impact it can have. But did you know that it can also have an impact on your turbo generator shaft line? How is this possible? Well, your turbo generator shaft line is of course connected to the grid by means of the generator. So every perturbation on the electrical side will be transferred by the generator onto the mechanical side. This also holds for the lightning strike. If this would hit one of the transmission lines, it would create a perturbation on the electrical side, which is then transferred through the generator on your turbo generator shaft line, which will respond in terms of torsional vibrations, which is a twisting motion of the shaft line. Now, normally a lightning strike and other typically occurring transient events like short circuits on the grid, they do not threaten the structural integrity of the shaft line. However, there are other interaction mechanisms that do threaten the structural integrity, and the probability of those occurring is increasing due to the ongoing grid transition. That's shown here on the next slide. So we have lots of changes on the electrical side on the grid. For instance, an increasing amount of renewables. We have much more solar farms, wind farms. And what they do is that they reduce, for instance, already the inertia in the grid. They don't have the kinetic energy that your turbogenerator shaft line itself has. So this means that when running through an electrical fault, it's harder to do so with these renewables. This means that they need to compensate, they need compensation for this reduced inertia, for instance, by adding more power electronics. In their turn, these power electronics can interact with the torsional vibrations of your shaft line. We have other changes, large distance connections in between countries. For instance, here in Belgium, we have an undersea power cable, a 1 gigawatt high voltage DC connection between Belgium and the UK. Of course, when this voltage is at land, you need to convert it again from DC to AC, and there you have a converter station, HVDC converter station, which converts again the DC to AC and vice versa. Again, this is control in a higher frequency range, which can match with the frequency range of the torsional vibration. So again, potential interaction, and there are a large amount of these converter stations being implemented as we speak. If the transmission line is not in high voltage DC but in AC, then typically the inductance of the long transmission line is compensated by series capacitors. And there again, you can create certain phenomena which can threaten really the structural integrity of your shaft line. We see some examples later on. Most of these phenomena are well known since decades, but some of them, like for instance interaction with a wind farm, are popping up. So there are also new phenomena. And the key point here is that while you're connected with your power plant to the grid, this grid is drastically changing, but you do not see it at your power plant because in fact you are blind. The power plants typically do not have torsional vibrations as a standard monitoring equipment. So this means that if something is happening, if an interaction is ongoing, exciting the torsional vibrations of your shaft line, you will not see it. Throughout time, the fatigue, which is caused by the oscillating movement of the shaft line, will accumulate fatigue damage. And so typically torsional vibrations are perceived as a silent killer. You do not see the damage happening, but when it happens and when the crack appears, it's too late. Some examples that we've experienced in the past, but also more recently, are seen here. So we will have more details on them later on, but typically what you can see is large cracks in main shafts of the rotor. So for instance, here in a compressor rotor shaft, you can see the typically 45-degree angle, which is also a feature of torsional vibrations. And the initiation typically occurs at a stress concentration. So typically in a fillet transition of one diameter from a lower one to a larger one. Besides main shafts, we also have cracks appearing in retaining rings, for instance, or in the generator slots. Some incidents have been reported as well of failure of blades, and we will have an example later on as well. So we would like to introduce now a poll, so you can answer directly in the poll that you see appearing. So how well aware are you that torsional vibrations pose a serious risk in power plants? So we'll give you a little bit of time to go through the answers and answer the question. checking if the responses are being received for the moment. Okay, we will close the poll and show the results. So thank you for answering. So here the results. Apparently, a large part of the people is well aware of the serious risks. So I fully understand the serious risks posed by torsional vibrations. So this is already a good sign. We will provide more details later on what type of risk you will see. 20% has never heard of the risk of torsional vibrations. So for those people, the webinar will present an interesting introduction as well. And some of them, 15% of the audience is well aware, but conceive it as a minor risk. So hopefully by the end of the webinar, we will have provided more information on the subject, and maybe this will change then your opinion of the webinar. So thanks for joining the poll. So let's move on. With my yes. So now let's go to the key aspects of torsional vibrations. So the basics. Most people are well aware and are more familiar with radial vibrations. So this is the vibration in the horizontal and vertical framework of your shaft line. This is a vibration which is felt on the casing. The excitation is typically due to unbalance. It's usually sufficiently damped, and you have your bearings that provide some damping due to the oil. And we have advanced criteria and standards. It's also closely monitored. So every shaft line typically has a radial vibration monitoring and or protection system. And people are well aware of the risk that radial vibrations can introduce. On the other hand, we have torsional vibrations, which is in a different domain. It's in the angular domain. So this means that your shaft is subject to a twisting motion, as also shown here by the moving image. It's a hidden vibration. If you enter the machine room, you do not see or feel the torsional vibrations. The forces are not transferred to the stator casing and to the surroundings. So you could be standing in a machine room and thinking, oh, my machine is running smoothly, while in reality, excessive torsional vibrations could be present. Typically, the excitation is external. So it typically mainly due to an interaction with the grid. They're very lightly damped because they're in the same direction as the rotation. So you want them to be lightly damped in that direction. Criteria and standards are not well advanced, and typically they're not monitored. It's not a standard part of your monitoring equipment. So how does your machine behave, deform in torsional vibrations? And we have the basic cylinder here. If we do a twist, if we deform it in torsional vibration, you can see that you have a twisting angle here represented on the figure. A turbo generator shaft line is more complex, of course, but in essence, the basics are the same. You have multiple natural frequencies, torsional vibration frequencies. For instance, you can see here the lowest one at 18 Hertz, and this is the first mode. And in that mode, the gas turbine behaves more or less as a rigid body and will be twisting against the generator. So you'll have a twisting motion of the gas turbine with respect to the generator at a frequency of 18 Hertz. This deformation, this movement is superimposed on a normal steady state rotation at 3000 or 3600 RPM. You have higher modes as well, as you can see here for a gas turbine. Here, for instance, for this example, 95 Hertz and 130 Hertz. And as you can see, for those modes, the deformation is more localized, for instance, to the gas turbine or to the generator. Typically, these higher modes are less excited by the grid, and so the most important modes are typically what they refer to as the subsynchronous modes, so modes below the grid frequency, below 50 or 60 Hz. If we then look at the stresses that are corresponding to this deformation, then we can see that these are mainly concentrated at the intermediate shaft. So here, for instance, for a movement at 18 Hz, the first node, we see that the main stresses are located near the coupling at the intermediate shaft. With a finite element model, and this is what we typically do if we engineer a protection system, for instance, we can also further detail the stress concentration at a coupling and then derive, based on the movement, what the stress in the shaft line is and where or how we would need to protect the system. Are there any questions? I don't know, Kevin, if you have.
Yes. We received already some questions. Thank you for that. I will, let's see. We have a question from Lionel. So are hydro units with lower rotational speed subjected to the risk of damages due to torsional vibrations? And have you ever experienced severe damages on such an asset? Fritz, I know that, okay, for a hydro unit, you have more damping due to the water and you have another generator, but maybe you can complete this answer.
Yes, so far we have not yet experienced any damage due to torsional vibrations on hydro units. And the main reason for this is that the generator is quite heavy with respect to the turbine for a hydro unit. So the generator for a hydro unit actually acts as a filter, and it filters everything that comes from the grid due to the high inertia of the generator. So it's very hard to transfer energy from the grid into the hydro unit.
Okay, next question from Olivier. Does the length of the shaft have an effect on the torsional vibrations?
The length, yeah, of course, has an impact on the behavior of the shaft. So actually, the dynamic behavior, like we've seen for the gas turbine, depends on the mass and stiffness of the entire shaft. So if an intermediate shaft, for instance, is longer, then you will reduce the rigidity of the shaft line and you will reduce the torsional frequency, for instance, of that shaft line. So the geometry has indeed an impact on the dynamic behavior.
Okay, maybe a last question, but don't hesitate to keep them coming because we have other moments where we will address to the questions. So how do you calculate the torsional natural frequency of a shaft line, or how are they measured?
To calculate them, we have software packages. So this can be a 2D package where you have cylinders, let's say, that are connected to each other, or a full 3D finite element model. So based on the technical drawings, you would then set up the model, and then you are able to determine the natural frequencies and the mode shapes. In terms of measuring, we will see later on that typically the existing speed sensors can be used. And so the existing speed sensors will then enable you to identify the torsional natural frequencies of the shaft.
Okay, thank you very much, Fritz. Let's continue.
Yes, so let's continue with some case studies. The first one is a very recent one, 2019, where we experienced a large crack in a compressor rotor shaft, actually near the coupling between the compressor rotor shaft and the HIP steam turbine. You can see here the crack appeared in a fillet, in a stress concentration on the shaft, and the shaft had to be replaced. There was an unavailability of almost 1 year due to the replacement of the shaft. So you can see the position, this was confirmed by a finite element model, but also the orientation at the 45-degree angle is a typical feature of torsional vibration, already suggests that torsional vibrations are present. And then later analysis actually showed that this phenomenon was already ongoing for more than 10 years. So intermittently, when certain conditions were present, the torsional vibrations were increasing. As you can see here below, for instance, in a temporary measurement campaign we performed, we identified these torsional vibration excursions. And so in certain conditions, this phenomenon was set in, accumulating fatigue damage, and over time creating, in the end, a crack initiation. The power plant was completely unaware. The shaft had to be replaced. The root cause analysis pointed towards field voltage control instabilities. So the power system stabilizer, which intervened in the field voltage control and actually amplified the torsional vibrations, in the end, initiating the crack. Similar incidents have recently occurred in other power plants. So the power system stabilizer will play a more important role in the energy transition because it stabilizes the power oscillations. And due to the upcoming renewables, we intend to have more of these power oscillations. So the power system stabilizer will have a more important role. The power plant was only alerted by the radio vibration monitoring system when it was already too late. So they tripped due to high vibrations. Another example is a well-known phenomenon called subsynchronous resonance. So it's typically interaction with a series capacitor bank, which is used to compensate the inductance when you have a very long transmission line. So for instance, we've been involved in a study in South America. First, there was a large incident, as you can see from the pictures on the right, in a power plant with several cracks after only 200 hours of operation of the power plant. And so after this incident, the TSO was aware of the risk and actually imposed the other power plants in the same country and in the neighboring countries to perform a risk assessment study and to install protection systems to avoid things from happening as we see here in the pictures. The phenomenon dates back from the 70s. It's well known, but it's not always taken into account in the design stage, or there might be some changes in the grid configuration which render the system unstable while it was stable before. Another example which is well known also typically in the design stage is excitation at twice grid frequency. So when you have a shaft line connected to grid, you will always have excitation at once and also at twice grid frequency. So this means 50 and 100 Hertz or 60 and 120 Hertz. So by design, you want to avoid that you have natural frequencies, torsional natural frequencies in that range. So typically you have a forbidden zone. For instance, here for the insurer of the nuclear plant we're considering here, it was between 98 and 102. But measurements revealed that we had a natural frequency very close to 100 Hertz, 99.5 Hertz. So this was not acceptable by the insurer. And we had to do a shaft line modification. So a theoretical model of the shaft line was set up. We did a shaker test on site to confirm the natural frequency. We did an impact test of the LP blades because these had a frequency close to the natural frequency, close to 100 Hertz, and could interact as well in the deformation. And so what in the end what we did is we added inertia at the coupling here between the LP turbine and the generator, which then deallocated the natural frequency from 99.5 to 98.5. You might say this is only 1 Hertz, but 1 Hertz in torsional vibration is really a lot, and this was actually sufficient to mitigate the risk. And then the last example is a failure due to interaction with a large consumer nearby. As you can see here, a crack which was initiated in a retaining ring of the generator due to important grid perturbation caused by an arc furnace for steel making. So these arc furnaces typically generate random fluctuations of megawatt and megavar, and then they excite the torsional vibrations of a nearby shaft line. Sometimes the fluctuations are then mitigated by power electronics. And again, these power electronics can interact with the torsional vibrations. So this is one example that we see here where again, the power plant was not aware, was only aware due to an increase in the radial vibration amplitudes. We performed a similar campaign, a detailed campaign at a power plant in Luxembourg, where we did both electrical and torsional vibration measurements and as well revealed clearly the impact of the arc furnace. So when the arc furnace was put into operation, there was a clear increase in the torsional vibration, and the analysis then led to a mitigation action, meaning that the electrical route in between the power plant and the electrical arc furnace was changed. So it was made longer in order to mitigate the interaction. So these were some examples, some case studies. We've been involved in more than what we can show here. It's not always possible for us to disclose everything due to confidentiality reasons, but there are more issues, events, incidents that have occurred. And the anticipation is that with the ongoing grid transition, the upcoming power electronics, renewables, we will have more of these incidents in the near future. So not sure if there are any more questions that have arisen.
Yes. Everybody responded very well to my when I asked that the questions. You can keep them coming. We have some very nice questions. We have a question from Leo, who's asking how can external effects influence the torsional behavior of VSDS-driven units?
VSDS-driven units. That's a variable speed drive units. Yes. And how can
How can the external effects influence the torsional behavior of these units?
Yeah, so typically these variable speed drive driven units are mainly excited by the variable speed drive itself. But this does not mean, of course, that the external influence is not important. So this is similar to other units. If it's coupled to the grid, it can receive perturbation coming from that grid. So interaction is still possible, although here, of course, the variable speed drive is the first to look for.
Okay, next question. The PSS is designed to stabilize the grid. So does it therefore destabilize the generator shaft line, compounding the problem?
Yes, so indeed the PSS, the power system stabilizer, is normally there to stabilize in a frequency range close to 1 Hertz. And so that's its goal, to damp the power swings that you have at these lower frequencies. But if it's not well tuned, or if the entire control loop and the field voltage control loop is not well developed, then you could magnify the oscillations in a higher frequency range. And so this is what we've seen. The power system stabilizer typically is, of course, it's not the intention to interact at this higher frequency range, and I mean between beyond 5 Hertz, 5 Hertz to 200 Hertz, if you will. That's not the goal of the power system stabilizer, but it can have an impact on these higher frequencies. So indeed, it can destabilize, and that's what we've seen in a couple of incidents quite recently.
Okay, thank you, Fritz. I will try to combine 2 other questions. There is a question about how do you derive the 3 different frequencies? I know you can even have more. And then there's another question, how is a shaker test done? So how do you derive these natural frequencies at the shaft, and can you explain how we do a shaker test on these units?
Yeah, so the natural frequencies typically, even without any excessive excitation, so you always have some noise on the grid, that's already sufficient actually to identify and to measure the natural frequencies. So it's almost noise, but it's still large enough to step out of this noise and identify them. So with a normal speed sensor on your shaft line, you're able to identify without having deliberately to excite these torsional vibrations. The shaker, of course, that's a means to deliberately, actively excite the torsional vibrations. We've used this once for the case study of the nuclear power plant, where we had an issue with a natural frequency nearby 100 hertz. And so there, the idea was to set up to instrument the shaft line with more sensors. And there we used the shaker to do a sine sweep. So the shaker would really only be used when you have a dedicated measurement campaign, but it's not always necessary.
And Fritz, was it performed on site, or did you need a specific location to do that?
Yeah, so the shaker, of course, was on site and connected to the generator end.
Okay, thank you very much. We'll proceed with the part of Enrique Moraga, who will present us the product range of Laborelec on torsional vibrations.
Okay, thanks, Kevin. Let's start with the last and more amazing part. Sorry, Fritz, for that. So you are going to discover what you can do to keep your gas turbine and steam turbine protected from torsional vibrations. Well, Laborelec and torsional vibrations have a long story together. Laborelec has been performing torsional vibration assessment and modeling for a long time. Back in the 80s, Laborelec started to perform the first measurements to check if a transient phenomenon had an impact on the torsional vibrations of a shaft line. Later, in the 90s, the criteria for torsional vibration became available. So I can say that Laborelec was one of the first companies in studying the phenomenon and the consequences in thermal assets. In 2000, Laborelec developed in-house the torso monitoring system and continued performing torsional vibration measurements. And in 2016, a catastrophic failure occurred in Latin America on a gas turbine with only 200 operating hours. After this major issue, as Fritz commented before, the subject became quickly a hot topic all over Latin America, to the extent that the grid operator obliged every power plant to perform a costly risk assessment or to install a torsional vibration monitoring and protection system. So at that time, Laborelec upgraded the device, implementing the protection feature, and the first Torso Protect was installed in 2017. Until now, more than 50 installations have been carried out worldwide, covering all different asset types. Also, we have been involved in many different phenomena, such as subsynchronous resonance in South America, subsynchronous torsional interaction in Europe, control instabilities with the PSS, and also two-time grid frequency excitation. I have to say that during this time, we have been involved in 6 root cause analysis for catastrophic failures caused by torsional vibrations, in which some of them, and that is one of the big problems, required almost 2 years for rotor replacement. So it was a really, really huge problem for the power plant. For sure, and of course, none of them had a torsional vibration monitoring and protection system like we are presenting here today. So our torsional vibration platform is called Torso, and it is the result of putting together the expertise and experience of high specialized teams such as materials, electromagnetic, EMC, vibration and mechanics, analytics, and digital labs, and others. And now, it is likely that you are asking yourself, what can I do to protect my power plant and stop being blind from torsional vibrations? Definitely, it needs to be one of our Torso products. Torso Protect, that is the first one, which is our full equipped monitoring and protection system. And the new one, Torso Detect, that is a low-cost system designed to detect if your power plant is suffering torsional vibrations. Let's go for the first one, Torso Protect. Torso Protect is a full equipped device which performs a continuous monitoring of torsional vibrations. It's a very advanced instrument which follows a strategy based on fatigue-driven protection. The system includes 2 levels of protection, an alarm and a trip, depending on the severity of the present torsional vibration detected. Both of them are activated when necessary. Regarding the installation, it is a standard 19 inches rack as you can see in the picture, and it is very simple to install. This is the most important feature, together with the fact that existing sensors can be used, not like other products that you can find in the market, which force operators to install additional sensor with a new connection cable, etc., would make the installation much more painful. It also includes analogs and digital output that can be easily integrated into the DCS. The digital ones are the alarm and trip, and the analog one is the torsional vibration amplitude. In this slide, you can see how easily Torso Protect can be installed in a standard 19 inches rack in a control cabinet. Also, you can see what the front and back of the product look like. As you see, it's really, really simple. We mentioned before that one of the main characteristics of this product is that the existing sensors can be used. Laborelec has developed an advanced signal condition device that reduces dramatically the sensitivity to the external perturbations, and it has also been optimized for pulse counting. Thanks to this design, we can use the existing sensor without any kind of problem. Again, this allows to make the installation very, very simple. So let's go now for the product of the day, Torso Detect, a development of Laborelec based on many years of experience in torsional vibrations. Why Torso Detect? In our discussion with customers, they were reluctant to install a torso protection system for the complete fleet. They installed for a specific gas turbine or steam turbine, but not for the complete fleet. Why? Because usually the cost considering the fleet was quite expensive. So there was a problem because the risk was still out there and the power plants were totally blind. Just a reminder that the lateral vibration monitoring system cannot detect torsional vibration. That is important to keep in mind. In addition, the risk is more and more increasing due to the grid changes. The power plants didn't have any way to know if they were under the impact of torsional vibrations. So, considering all of this, Laborelec had designed a low-cost, game-changing product for torsional vibration detection. This system has been designed for detecting torsional vibrations in power plants in such a way the risk can be mitigated. The system allows operators to know quickly if their turbomachinery is suffering torsional vibrations. When this happens, those torsional vibrations must be analyzed to assess how they are impacting and if the turbomachinery is in danger. At that point, we can support as well with a temporary campaign realized with Torso Protect, our product just presented. Well, Torso Detect is a low-cost solution for detection of a normal torsional vibration. It shares many of the characteristics of Torso Protect. In this case, the device is continuous monitoring of torsional vibrations. The torsional vibration amplitude is easily integrated into the DCS or in a general monitoring system, which is already installed in the power plant, like System 1 of Bentley Nevada or others. Regarding the installation, it is really simple, plug and play, that can be easily installed by power plant operator and supported by us remotely. Unlike Torso Protect, existing sensor can be used, and not new sensors are needed to be installed, thanks to the galvanic isolation and signal condition previously explained. So, as a summary, Torso Detect in a nutshell, we could say that it's a low-cost, robust system. It's very simple to install, plug and play, no new sensors are required. The installation can be made by the operator. In fact, we are going to provide an installation procedure and a video to make it possible. The data available in this equipment as an output can be easily integrated into the DCS or even in the lateral vibration monitoring system if there is already one in the power plant. I'm going to say that we are very happy to announce that we have already received the orders for 18 units to install in the next few months. And I would like to be contacted by that, for example, that 15% of the people that in the poll have said that they know perfectly, they fully understand the risk of torsional vibrations in the turbo machinery. So we will be very happy to explain more about this product. Just finishing, I would like to remark about Torso Detect that is the perfect solution that allows operators to keep the power plant safe with a very low investment. So thank you very much.
Yeah.
And now, Kevin, if there are more questions.
Thank you, Enrique. There are two more questions that we will speak about. So, Fritz, what is the typical amplification factor for torsional natural frequencies with membrane type couplings or disc stack couplings?
Yeah, interesting question, but I'm afraid the answer will not be that concrete or easy. Yeah, those are two components which of course have their influence on the dynamics of a shaft line. The amplification factor is typically only depending on the damping of your structure. So if you're in a resonance condition, if you have an interaction and you're exciting the shaft line at a natural frequency, then your amplification depends only on the damping within your structure. So a coupling can provide some damping, and then of course this amplification depends on the damping specifications of the coupling, but also on the other damping introduced by the grid itself, for instance, or other components on the shaft line. So it's really case specific. It's a difficult one as well to assess, and there's no clear modeling or theoretical modeling for damping to know what really the amplification factor is. But the best way is still to measure.
All right. Next question, maybe with a more straightforward answer. So once torsional vibrations are detected, what measures are taken to reduce them?
Yes, once they are detected, this means that there are important amplitudes which might threaten structural integrity of the shaft line. Then of course it depends on the root cause. And so a next step would be to then do a more detailed measurement campaign of the power plant, for instance, where you correlate with nearby large components on the grid, which might introduce an interaction. You're of course only monitoring at the power plant, so it could come from everywhere, but already the single line diagram can provide you some ideas. Also, electrical measurements in this case could also be used to identify any control instabilities. If it's a control instability, a change of a parameter, a gain, for instance, in the control could already mitigate the amplitudes. If it's really an interaction with a component outside, for instance, a series capacitor bank or a converter station, then measures needs to be taken at that component, for instance, preferably to avoid further damage.
Okay, thank you, Fritz. Another question. When the shaft line has a gearbox between the steam turbine and the generator, does it have a particular effect on the torsional vibrations?
Yeah, shaft lines with a gearbox are more complex, let's say, than shaft lines without. If you have a gearbox, then this means that you have a coupling already between the radial vibrations and the torsional ones. So there, let's say the advantage would be that if you have an increase in the torsional vibrations, you would see it in the radial vibrations as well. So your radial vibration system could be used, let's say, as a detection, in this case, for torsional vibrations. Of course, you need to know which frequency you have to look for, but that's already one of the differences with a normal shaft.
All right. Maybe one more. How is it possible to select the best locations for the sensors of a torso system?
Yeah, that's a good question, because typically we're not able to put a sensor everywhere we want. As already mentioned, in 90% of the cases, we're able to reuse the existing sensors. So this means that the existing sensors are typically well positioned. In some rare cases, unfortunately, then it's not the case. And then we base ourselves on the model, the theoretical model of the shaft line, so the deformation. If you think again about the 18 Hertz deformation, the gas turbine twisting against the generator, there the shaft end would be a very good location for detecting that mode. So it depends, of course, also on the frequency. If you have really issues at higher frequencies, then you might need a different location. But most of the time, the location of the existing sensors is okay. You don't need to be at the real maximum. As long as you can detect the vibrations, then you're good to go.
Okay, final question. I have a question from Rahul here. Is torsional vibrations, will it be impacting the wind turbines and their generators?
Yeah, wind turbines. So we've been involved as well in a measurement campaign, a research project on wind turbines as well. And so the impact thereof on wind turbines. Typically, the wind turbines have a much lower natural frequency and torsional vibrations. And therefore, what we see for the moment is that the concern is more on the electrical level. So the mechanical level, let's say, is less concerned, although there, if you have a gearbox, the gearbox might be subject to large oscillations, so that might reduce the lifetime of the gearbox. But typically, as what we've seen, is that it's more electrically. There is a new phenomenon, sorry, which has popped up quite recently, where you have interaction between a wind turbine farm and a power plant, a conventional power plant. So that's also interesting, that those are phenomena that were not known before and that are now popping up, new phenomena, which are left unidentified, if not monitored, of course.
Okay, thank you, Fritz. Thank you, Fritz. We will conclude our webinar here. If during the coming days other questions arise, don't hesitate to ask them through email. As said, all questions will be answered through email. So if you want to, or if you want to be informed about other webinars from Laborlec, you can register yourself to our mailing list. I also want to take the opportunity to invite you to the NLIT Fair in Milan at the end of the month. There we will present Torso Detect with the demo. We will also have a booth, so please come and visit us, and then we can give you additional explanation, and we can show the system operational. And also in 2022, we're really looking forward to that. We're taking part in the Torsional Vibration Symposium in Salzburg, Austria. So yeah, we're looking forward to that also. So that's it for today. I hope you enjoyed the webinar, and thank you for your time. Bye-bye.